And we're away. So hello to you all. This is Eamon Darcy from QEQA, the Quantum Education Centre of West Australia, and I'm the founder and operator of it. And I love anything to do with quantum physics and quantum computing. I feel rather fortunate that I've got into, well, I have a master's in e-commerce where I did encryption, but I do feel as though I'm lucky because I'm coming from the physics side, whereas most people are just in the IT area and they think it's, oh, quantum computing, yeah, that's one more step or whatever, whereas it's totally different. And it's important to keep that knowledge of quantum physics going, you know, like the double slit experiments. And if any of you log on to the QEQA website, you'll see 3 pivotal experiments there that I talk about. The double slit, the delayed choice quantum eraser, which actually proves that time, it actually proves that events that have already happened can be altered in the quantum world. And then you've got the Harriet-Watt experiments conducted only 1 year ago in Edinburgh, which prove objective reality doesn't exist. We sort of build our own universes, but that's a different subject. But do get in touch with me if any of that interests you. But this is a great presentation. I love this presentation. And as I was just mentioning before, what Deutsch's Oracle does, it's the basis for almost all algorithms because it shows, well, it shows 2 things. One, it shows how a quantum computer can compute exponentially quicker than a supercomputer. I used to always think, how can it be so much quicker than the supercomputers of today, which basically run at the speed of light? So how can it be quicker? And the answer is it can, because it requires exponentially fewer processors. In fact, it's all down to superposition, as you'll soon see. Now, it's relatively complex, so I'm going to go relatively slow, but please ask questions. I'm here on my own, so you can either unmute yourself or send it through the chat. And as soon as I see anything in the chat, I'll have a look and answer the question, because I do think this is something that you need your questions answered immediately. It's no good waiting till the end because you've lost the flow of it. But it's important you know this. It is complex, but you'll get there very easily. So, Deutsch's Oracle. Now, there are 4 functions, and I'll assume you understand what a qubit is. There are 4 functions you can execute onto a single qubit. Oh, I've just got a question. Oh, it's just a hello all. Well, hello to you, Temi. There are 4 functions you can apply to a single qubit. When you've got 2 qubits, you can do more. You can do AND or C naught, etc., etc. But the functions on a single qubit, there's only 4. I'll show you what they look like on a quantum computer, and then I will show you this very, very clever oracle that David Deutsch came up with. It's fantastic. And then I'll prove it all to you sort of mathematically, and then hopefully we can discuss it. Very exciting. So 4 functions on a single qubit. They are, I could have asked you, but here we go. They are identity, negation, constant 0, and constant 1. So think about it. We've got a qubit that can be either initialized to 0 or initialized to 1. We then put a function on it. So you've got the input qubit, you've got the black box, we call it the black box, I'll explain in a second, and then you've got whatever the output is. So the input, if it was a 0, let me just get my marker up. Oops, sorry. So I'll get the spotlight up so you can see where I'm going. So if it's an identity, everything just remains the same. So you've got your one qubits, either a 0 or a 1. If it's a 0, and let's say the function is identity, then it comes out 0. If it's a 1, it comes out a 1. With negation, it's exactly the opposite. If it goes in a 0, it comes out a 1. If it goes in a 1, it comes out a 0. And then you have your constant 1. So that is sort of like, no matter what you put in, we don't care what you put in. Whatever you put in, the output will be 0. And vice versa, whatever you put in doesn't matter. The output will be a 1. So it's constant 1, constant 0. Now, let me just ask you something now. So I'm going to ask a question. If you could answer in the chat, it'd be really excellent. But how many goes do you think it would take a classical computer? How many goes would it take a classical computer before you could identify the function? So does anybody want to have a bit of a guess at that one? 2, thank you, Joachim. Score, I think that's 2 people. Yes, thank you. Now, how many do you think you would need for a quantum computer? I love it. You guys all know. Well, not 2 to the end. Good answer, Tammy, but no. But Score and Joachim, I think you're 2 different people. You're dead right. So you guys know what you're talking about. It's 2. Most people, of course, say 1, but it's actually 2 because there are 4 functions and you've only got 1 qubit. And the reason why I wanted to mention that is because let's not think that in the quantum computing that it can multitask to 4 or do all these things at once. It actually can't. It can only be 1 or 0 when it's actually measured. So in between that, in superposition, it can be an infinite number between 0 and 1. Quite often you'll hear people say, and this is quantum physicists as well, they say a qubit can be 0 and 1 or 0 and 1 at the same time. Hi, Sharon. It's actually a lot more than that. And that's not a good enough statement. It can be anything between 0 and 1, dictated to by the Bloch sphere. And I think I've done a presentation on the Bloch sphere, but if you really should understand the Bloch sphere the further you go. But great answer, you guys. It takes 2. But now, I'm actually going to give you a bit more information now. So remember the 4 functions. 2 of them, the identity and the negation, are variable functions. And constant 0 and constant 1 are constant functions. You may hear them being called constant and balanced and etc. etc. It doesn't really matter. You can call them Tom and Jerry if you want. But identity, negation are variable. Now, identity negation are reversible. Now, all quantum operations, functions, gates have to be reversible. And that's just a product of physics. There's no getting around that. And all reversibility means is that if you know the outcome, like in this case, you know the output qubit, and you know the operation, and you can work out the input from those 2, then it's reversible. You see, and with constant 1 and 0, they're not reversible. If I put a 0 in and a 0 comes out, well, we don't know whether it's identity or a constant 0. So, yeah, if the function's a constant 0, it's not reversible. And that's a very, very important point. So let me just explain the whole point of what we're trying to do in Deutsch's Oracle. I give you a gift of a black box which contains one of the 4 functions. So I'll just get my marker up. I'm giving you the black box here, terrible gift, I know. And inside there is a secret. It's one of those 4 functions. Now a 1 or a 0 goes in, it's operated on, it's multiplied by whatever, one of, whatever is the function in the box, and then a 1 or a 0 comes out. Now, back to the chat and the guess. So a question, how many goes do you think? What we want to know now is whether it's variable or constant. How many goes would it take a classical computer to work out if it's variable or constant? 2, thank you very much. And how many goes would it take a quantum computer to work out whether it's variable or constant? 1, exactement. Exactly, and this is the beauty of it. It's David Deutsch has said, hold on, we only need 1 process to work out whether it's the type of function it is. So in one go, we can't tell you which function it is, but we can tell you the type of function. Now that is incredibly important for future algorithms like Shor's and almost all of them. I can't think of one that doesn't use this ability to work out. I mean, that can now work out a certain type of function. It can work out whether it's odd or even. There's many, many things it can do. And I'm going to show you how it does it. Now, it does get a bit confusing, so let's just see how we go. Okay, so the challenge is that you must ascertain whether the function inside the black box is constant or variable in one go. You can't do it with a classical one, but using the quantum force of superposition, we can do it, thanks to David Deutsch. And it's undeniably faster. And the idea is with Deutsch-Jozsa algorithm, which is the continuation, the evolution of this. Deutsch's Oracle was first done in 1993. And then in 1994, a slew of, including Peter Shor's algorithm followed. And, there's no question this was the predecessor. Because even though we're going to do it with 1 bit, which is exciting enough, you could actually do it with 2 to the n being the number of qubits. And if you've got 40, 50 qubits, which already we have computers that do have that, even though they never compare quantum hardware by the number of qubits, because it depends whether it's annealing or whether it's gate-based, and then it depends on things like the validity of the gates and many, many other things. But with 30 to 40 gates, the number equals the amount of stars that are on the sky. And that's how many times it would take, nearest damn it, a classical computer to do something. And we're talking about the fastest computers on Earth. But even if it's 2 to the 300, a quantum computer can do this in one go. That's how amazing it is. Fantastic. Okay, let's get down to the nitty gritty. Now, please do ask questions. Are there any questions now? That's fair enough because we haven't really got to the hard part. Okay. In order to facilitate Deutsch's Oracle, we need to establish another qubit on the line. So, whereas before we had one qubit, we're now going to be using 2 qubits. It's not cheating. It's 2 qubits. One is an input qubit and one is an output qubit. Now, I'm telling you, and this is the bracket notation, I'm assuming you know that with the input and the output qubits, and here's the values of them. I'm telling you that if the output shows a 0, 1, that is the input 0 and the output's 1, then it will be a constant function. And if it's a variable function, the output will always be 1, 1. So let's see how we go with that. Now, I'm going to show you the gates that are necessary to portray the 4 functions I've given you. Sorry, this is just showing. So before we had the 1 in and 1 out. Here we've got 1 in, 2 in, but the output here is initialized to 0 always. And then once it comes out of the black box, it shows the output, which is the input, which could be 1 or 0, times the function, which is inside the black box, which can be one of those 4. The input is never altered. So are we all okay with that? It's just changing the ballpark a little bit. And the reason why we do this, is to simulate reversibility. So this enables us to make all of the functions reversible. Yeah. Okay. All right, this is where you've really got to pay attention. Constant 0. Constant 0, we do nothing because we've initialized this is the output qubit and this is the input qubit. So it looks a bit strange that this is it, the output input. This is it going in, even though it's called the output, but it's been initialized to 0. So obviously we just have to leave it. So we actually do nothing. That's easy. When we want a constant 1, what we have to do is make sure that the output is always a 1. So this function here will be the constant 1 function. And the way we do it is we put a negation gate, which is just a bit flip on the output qubit. So it now goes in, it's flipped, so it goes in as a 0 because we know, in fact, all quantum algorithms, the input's always initialized to 0. And it's just a function that we follow. It doesn't have to be that way. The more complex algorithms don't actually start with a 0, but we won't worry about that now. But if we put in the 0, so we know what it is, we know that if we flip it, it'll always be a 1. So we've got the output qubit right, and it's a 1. So that's our function, where we're going to use the constant 1. Okay, now we've got the identity. That's where we keep it the same no matter what happens. Now for this, we need what's called a CNOT gate, and I have to assume you know what that means. If not, you needed to go to some of my earlier presentations on quantum gates and linear algebra, but it's dead easy. It just means that on the input qubit, we put a control bit, and then there's a target bit there. So when it comes in, what will happen to CNOT, if it's a 1, it will flip the output. If it's a 0, it won't. So let us go through that. Now, if it's a 0, and then and it hits the CNOT gate, it's just going to stay as it is, a 0. It will stay a 0. But if it's a 1, it will, on the input line, because remember, that's the input is always the 1 or 0 that you're putting in. If it's a 0, it'll return 0. If it's a 1, it will flip the qubit that we have initialized as 0. And then that will make it a 1 so that the identity has been kept. Okay, so far. Please don't hesitate to ask a question. It does get a bit, it's not complex, it's just difficult to keep up with. So, with negation, what we do is a CNOT followed by a negation gate, okay, which is a NOT gate. So it flips it. Okay, so if it's a 0, then nothing will happen. But so if it's the input is 0 and there's a control NOT gate, so what happens when it hits the control NOT gate? If it's 0, it's going to go straight through to here, and then it'll flip to 1. So it's gone from 0 to 1. And then if it's a 1, it's then going to flip this one to a 1 at this stage with the CNOT, and then it's going to flip it again back to the 0. I think I've mixed that up. If it goes in as a 1, it'll change that to a 1 because it flips it, and then it's going to flip it again back to a 0. So you've got your negation there. So that's what the 4 gates look like. Do nothing, have a bit flip, have a CNOT gate, then have a CNOT gate and a bit flip. Okay. Now we need the oracle. Here is the oracle. So this is what David Deutsch came up with. This is the algorithm that no matter what you put in, it will be able to identify whether the function was a constant or a variable. And I have to assume you understand what a NOT gate is and a Hadamard gate is. A Hadamard gate merely puts it into superposition. And, this is where it gets a little bit complex, of course. So here's the proof of concept. Here, I'm now going to prove how those gates, those functions, and I'm going to apply every one of them to every possibility of 0 and 1, and show you how it will return 0, 1 if it's constant, and 1, 1 if it's balanced. Now, before I do that, just to make it easier, I'm going to show you what we call the state machine. I don't know whether you're used to these, but it just makes it very easy to apply functions onto this is essentially a block circle. So, and again, I have to assume you understand a little bit of linear algebra. But here we've got for the x, for the NOT gate, it will go from 1 over square root 2 minus 1 over square root 2. Now, we always start from here, and let me show you why. Because the way the Deutsch's Oracle works, in fact, the beauty of it, as I say, it's all superposition. So what it actually does is it gets, instead of putting a 0 in, it operates on the 0 first. And then it enters the black box to be operated on by whatever that function may be. So it's a not, so both are initialized to 0. It goes in as a 0, it's flipped to a 1, because that's the NOT gate, so whatever comes in, it'll change it. And then we have the Hadamard gate, which puts it into superposition. Now, because this is a 1, the superposition, if you put in a 0, and this is, again, just things you have to understand, if you have a qubit initialized to 0, and you put it through a Hadamard gate, it goes to 1 over square root 2, 1 over square root 2. If you have a 1, it goes to 1 over square root 2 over minus 1 over square root 2. What it's doing is it's changing the phase. But by changing the phase, it enables this wonderful thing to happen that we can perform this in one go. So I'm telling you that that when we put the qubits into the black box, they will now be not 0, but they will be down here, 1 over square root 2 minus 1 over square root 2. Now, this shows us what happens with a bit flip at all the different states we can be in. 1, 0 is 0. And if you put a bit flip to it, it'll go to 1, as we know. So this is what happens. We can use this to quickly work out what a NOT gate effect will be. And that's rather easy, but the Hadamard can be difficult. So if we apply an Hadamard to a 1 over square root 2 minus 1 over square root 2, it will go to 1. It's reversible. And if you've got it at 0, it will go to 1 over square root 2, 1 over square root 2. Okay, so you just take it for read that that's what happens. Any questions so far? Okay, let me keep going. Now, here we're going to get to the proof. Oh, so here's what I just mentioned before. This is the pre-processing. So this is the bit flip and the Hadamard. And that's, as I said to you before, it's initialized to 0. It goes through the X gate, and then it goes through the Hadamard gate. Notice the minus. So it enters, I'm stressing this because it's important, because this can be confusing. So when it goes into the black box, it is not a 0, it's the square root of 1 over square root 2 over minus 1 over square root 2. Okay. So here's the state machine. This is what happens. I need to get these out of the way. You can see the result here is 1, 1. So what's happening with when the constant 0, where you may remember we're doing nothing to it. So if I go back, and I know this gets a bit complex, so try and stay with me. So here, we're going in here as 1 over square root 2 minus 1 over square root 2 goes into the black box. Now nothing happens because that's what we agreed is the function we use if we want constant 0. So it comes out, then it goes through a Hadamard gate. So what happens if you apply a Hadamard gate to a 0? And sorry, I should have said before, this is when you measure it. Now don't forget, when you measure it, all the superposition, whatever a superposition is a complex form of the probability of being 0 and the probability of being 1. And the probabilities are complex amplitudes. And that's the whole beauty of superposition. Whereas in the normal world, if you say there's a 20% chance of it raining tomorrow, then we know there's an 80% chance that it won't rain. But in the quantum world, you can actually say which you couldn't say, I couldn't say to you, there's a minus 15% it's going to rain tomorrow. That just doesn't make sense. So the superposition is brilliant. But when you measure it, it goes to 1 or 0 with equal probability. And you don't know, and you never ever will know, what those complex amplitudes, the square root of minus 1 chance that it's going to rain, you will never know that minus 1 over the square root of minus 1. You will never know what state it was in once you've measured it. So with the constant 0, we know it's going in as 1 over square root 2 over 1 over minus square root 2. Nothing happens to it, but then we apply a Hadamard gate. So going by our machine, if we put a Hadamard gate, and now we're looking at the input qubit and the output qubit. So the input qubit's the bottom one, the output qubit's the top one. The input qubit never changes in theory. So we're putting it in as 1 over square root 2 minus 1 over square root 2. It hits, nothing happens in the black box. It comes out and it hits the Hadamard gate, and then it's measured. So when it hits the Hadamard gate, this is the action that the Hadamard will have on this function here, which we know because it said before in the state circle. So it will go to 0. It'll go to 1, sorry, 0, 1 is 1. So the input qubit will be 1, as we can see there. And the output qubit goes to 1. So we've got 1, 1. So the balanced function, like I said before, would always be 1, 1. So we've got 1 out of the 4 ready, right. Any questions? Let's look at constant 1. Now, constant 1, let's remember what we had for constant 1 is just a negation gate, a NOT gate, a flip gate, a bit flip on the output qubit. So, when we come back here, we do, before there was nothing in the black box, now there's a bit flip. So let's have a look at how that bit flip on the output qubit, nothing happens to the input qubit. that again just has there's no, the black box just affects the output qubit. So this is just affected by the Hadamard post-processing after the black box. So we know that goes to 1. And now we have the output qubit. Well, remember there was a bit flip. So the bit flip will change the 1 over square root 2 minus 1 over square root 2. If we bit flip it, it goes to minus 1 over square root 2 over 1 over square root 2. And then that's the process in the black box. Then it has to go through the Hadamard gate, and that brings it to 0 minus 1. And when you square these out to actually, you've got to square them to see what they are, that will equal 1. So again, we have a constant and it's 1, 1. So we're doing well. Any questions? We've got 2 out of 2 so far. Now, this is the tricky one. And if you're looking at this for the first time, you're not going to get it, but you're going to have to ask me questions and questions, and then it'll come to it, because this is strange, and it's a strange effect of superposition. So you might remember the identity was the C0 gate. Let me just make sure. Yeah, the identity is the C0 gate. Now, remember I said the input qubit never changes. Well, we've got a question. We've got a, sir, are you going to share the slides with us, Tammy? Yes, I am. I will not only share the slides, I will share the recording. And you can also ask me any questions from the group. So you should have my email address. If not, ask me for it. My pleasure, Tammy. And I'm also eager to chat with any of you and have a Zoom with you individually to get, so that you understand. For me, yeah, look, I'll put my email in. I'll put my... darcy.amen@gmail.com. Now, please mention, if you email me, and I want you to email me, if you email me, please say that you're part of the Quantum Computer Australia group. So, okay, but this is difficult. Try and remember, so with the input, so the black box has a C0 gate in it. So very strange things happen with the C0. It actually, and I'll mathematically show you in the next slide how it happens. If it's confusing, I'd rather you just accept it. I do this a lot in quantum physics. Just accept that it's the way it is, and then understand the whole concept of everything, and then go back and work out what exactly is happening. I don't want you to get hung up on this, because it's just an aberration. Okay. So, amazingly, when we have a C0 gate, it actually changes the input qubit. And the input qubit goes from 1 over root 2 minus 1 over root 2 to 1 over root 2 minus 1 over root 2. So, not minus, sorry. 1 over root 2, 1 over root 2. I was just thinking what was happening there. And then when I apply the Hadamard gate to it, after post-processing, it goes to 0. And this notation, 1, 0 is 0, 0, 1 is 1. You should know that. If you don't, we need to talk more at a basic level. So that's gone to 0. Amazing. Now, with the top output, all it's done is, if it's a 0, the CNOT gate has no effect on the output qubit. So there's just the Hadamard, which takes it to 1, because it's going in as 1 over root 2 minus 1 over root 2, takes it to 1. Therefore, we have the input qubit is 0, the output qubit is 1. 0, 1. So we're now 3 for 3. Now here's, and again, don't get hung up on this. This is the mathematics of the how the input is changing the. As I say, it's an aberration that when you've got 1 over root 2 minus 1 over 2, 1 over root 2, and you've got its tensor product. So you've got the input qubit here, the output qubit there, and you multiply them together, you come up with this. This is the CNOT gate as a matrix. All gates can be portrayed as a matrix because that's what's happening. It's all matrix multiplication, and you need to understand your linear algebra to follow that, but it's honestly not complicated. And then that equals a half over 1 minus 1, 1 minus 1. And we can factor that out to the input output. Now, if we ignore everything in the middle and we just look at here, we can see that the output qubits remain the same and the input qubit has changed its phase. And that's the key. Don't worry too much if you don't understand that. We can go over that. I like to include here a very useful slide, which is all the gates, not all the gates, but many of the most used gates and how they translate to a matrix. So we were looking at the CNOT gate then, and that's why that matrix came in. This is a very useful slide to have, I find. I'm constantly referring to. Okay, any questions? I can't remember if I've done all 4. No, I haven't done, but this is the 4th. So now we have the negation, and we just remember the negation should be CNOT bit flip. Yeah, so just to remember, negation is CNOT bit flip. So that's what's in the black box in this instance. So we can see that the same thing happens because nothing's changed with the input qubit. So that strange aberration still takes place. But with the output qubit, we have the bit flip in the black box, and that will, sorry, where's my spotlight? We have the bit flip followed by a Hadamard. And it goes to -1, which means we have 0, 1. Unfortunately, you can't see with that in the way, but so we have 4 for 4. Every time it was 1, 1, it was balanced. Every time it was 0, 1, it was a negation gate. Wow. Trust me, that is so important. It allowed us in one operation to work out, through the wonder of superposition, it allowed us to work out the nature of that function. Unbelievable. And again, we're only, well, I'll remind you here. So by Examining the result, we can determine the constitution of the function, whether it's a constant or a variable. I've shown that to you. Now listen, please listen. Even if you haven't understood that, trust me, you will. If you go over it time and time again, after 2 or 3 times, trust me, it makes sense. And it's beautiful. And David Deutsch is a legend from Cambridge. He really is. But even if you don't understand it, look at this. Because what we've done is, it's rather like how a magician forces a card. So you choose a card. What we've done in effect is we've neutralized the effect within the categories. So within variable, we have, the only difference between the variables is a negation gate. So that's reduced the effect between the categories. Now, within the categories, sorry. But then we've magnified the effect between the categories with the C-not gate. Now, when you talk about any optimization, when you're doing a gate-based algorithm, you'll normally get the exact answer. Like something like Shaw's will give you the exact answer. But with optimization, you tend to just get, you narrow down the issue, if you like, and that's good enough. And particularly with optimization problems. So what this is doing is pushing up the correct answers. Whatever answer we're looking for, we can fix the oracle so that it will magnify the correct answer while negate the wrong answers. And that's all done through phase as well. So we're actually having constructive phase, adds it together and makes it bigger, and deconstructing the phase negates it completely. And it was Deutsch's did this oracle with it's pretty contrived. He had no practical idea in mind. But then, of course, we had Simon's periodicity problem, which is involved with factoring and many other things, and also Shaw's algorithm. Now, to give you an idea how important Shaw's algorithm is going to be, next time you go to the ATM, now that's an automatic teller machine. I think you guys in America still call it ATM as well. But anyway, where you go, you get money out of. Your PIN number goes into a hash, and then it's encrypted, sent to the bank, decrypted. Your PIN number is verified. You're good to go. The transaction is approved. Now, the fastest supercomputer in the world, if it got hold of that transaction, it could work out your PIN, but it would take literally, not figuratively or metaphorically, literally thousands of millions of years. So you're safe. Computers are very, very good at multiplying 2 numbers together to equal another number, but they're very poor at working out what 2 prime numbers equal this other number. So, you're safe, and everybody uses it. It's called RSA. All ATMs use it. Almost all social media uses it. But we're safe, because if somebody even did want to intercept the transaction, it would take them that long. But with Shaw's algorithm running on a pure large quantum computer that doesn't exist yet, at the moment we've got called NISQ computers, noisy intermediate scale quantum computers. But we would need to do Shaw's, we would need FT computers, fault-tolerant computers. So they're pure qubits, and if we had a large one, it could detect all the PIN numbers on Earth in 6 seconds. So that's how it's going to change the world. Okay, everybody, that's the end of the presentation. Now, I do hope we have some questions. Do we have any questions? You can either unmute yourself, you should be able to unmute yourself, or you can just put it into the chat. Joachim, you must have a question after those great answers. Are we saying that all 7 of you followed that process? I'm happy to believe it.
Yes, we do, but I'm just thinking that, we have to go through it one more time.
Oh, absolutely.
To really grasp it. What is just confusing me is the aspect that you talk about, the reversibility.
The possibility, did you say, sorry?
The reversibility.
Oh, reversibility. Yeah, that's
because some materials that I read was that discussed quantum computing in terms of the cryptography.
Yeah.
Is telling us that one of the key things that quantum computing would do well is that we can be able to trace anything that any hacker, maybe any impact on the key, the cryptographic keys, can actually be detected that maybe it has been tampered with.
Yes, it can do.
Yeah, through the properties of reversibility.
No, not that. Well, not directly through that.
Okay.
Well, yes, in a roundabout way. I've also done a presentation on quantum teleportation. I don't know whether you saw that, which is a lot to do with cryptography as well, because it's basically sending the superposition over long distances. But yeah, it can tell whether it's being looked at by an intervener, whether somebody's tried to look at the communication, but that's not reversibility. It's not because of reversibility, although reversibility is a part of the reason why that happens. It actually collapses, the communication collapses if somebody tries to get in on it, and then that stuffs everything up. But let's leave that for the moment. But reversibility is a very, very important concept in quantum computation. And all algorithms have to be reversible. And again, just to explain, a reversible one is where if you know the output and you know the operation and you can work out the input from those two, then it's reversible. And that's very important. So thanks for that question. Saban, I was late, unfortunately. I want to watch the recording later. You certainly can. Score, just want to say thank you for this wonderful presentation. How kind of you. Please all, I have a number of students and they're always amazed by how much I love to get questions. So don't think you're being a nuisance or anything. Do email me and I will get back to you. I give you my word of honor, I'll get back to you. And if necessary, we can have a one-on-one Zoom, free of charge, a one-on-one Zoom so that I can get the point over if it's quite complex. But Joachim was quite right. It is something you have to go over 3 or 4 times. It's not easy, but by the same token, paradoxically, it's not difficult either. And by the way, talking about quantum teleportation, as I was before, the one thing I always stress, and the one thing that still amazes me, is how easy it is. It's obviously a very, very complex process, because you're sending complex amplitudes of a superposition, which you're not allowed to look at, and you're sending them thousands of miles. And you're not allowed to know what they are or look at them. So it's very difficult to process. But the number of boxes, it really is just a C0 gate and a thing called a Bell state. And you probably know what a Bell state is. It's just a NOT gate and a C0 gate. And a Hadamard gate, sorry. No, a Hadamard and a Hadamard and a C0 gate gives you a Bell state. Irrespective of that, it's just a couple of gates and then a couple of classical bits. And because of the wonders of superposition, we can effectively teleport an atom to an atom on the moon and give it the exact same quantum state. Amazing. And only through a few gates. Now here, we're able to do something that would take thousands of years on a classical supercomputer, we're doing in one go. It's amazing. Look, thank you very much for your attendance and your time. I will be sending to the group the recording, the presentation, and please feel free to contact me. Thank you all very much.